Okay, it's my pleasure to introduce Professor Keerthi Madapusi from Boston College, and he's a recipient of different shares of Science Award, and he will talk about types of C and abelian varieties and special cycles.
Okay, so, oh, that's very loud. Okay. Is that okay if I switch it off? All right. Okay. Um, so take logarithms, and there's a formula of Lurch that basically reinterprets the right-hand side in terms of the Dirichlet L function of chi. Okay, so very classical, involves reasonably elementary things, but this was reinterpreted, I think, by Gross, or maybe initially. Yeah. So, in terms of things you might call, depending on your perspective, more geometric or maybe more arithmetic, instead of just being something from analytic number theory. So, to do this, we have to introduce a notion of a metrized line bundle. So it's just one projective module. So this is a number field and a ring of integers, so it's something that you can do the following with. Namely, you can associate a degree to it. So if you in the theory of Riemann surfaces, like a very important fact is that if you have a line bundle on a projective Riemann surface, you can associate a degree with it. If this analogy between number fields and function fields, of course, this is classical dilemma that spec Z is not compact, and so there's no good notion of a degree for a line bundle over spec Z. But then, or spec OL in general over here, and it's okay. So this is some solution which you have introduced all the places at infinity that functions as some kind of compactification, and so the integral structure is replaced at infinity with a metric, so for any metrized line bundle, you can associate this quantity, which depends. Okay, the formula on the right-hand side seems like it depends on this choice of a non-zero section, but because of the product formula, you see that in fact it's a canonical quantity. So this is independent of the choice of this section. Okay. So now we can reformulate the left-hand side of the Challis-Elbert formula. So if you remember, it was sort of this quantity over here, and at least to me, it's a little mysterious. I don't know. So until I saw this perspective. So if you take an elliptic curve over the ring of integers, so by which I mean, so it's an elliptic curve over its over the field L, which has good reduction everywhere. Then you can take its canonical bundle, which is just a bundle of one forms on it. Okay, it's a rank 1 projective module over OL. You can give it a canonical metric at each place. Basically what you do is you have this elliptic curve, you use an embedding of sigma to get a complex manifold, this Riemann surface, which is a torus, over the complex numbers. And then now I have a one form, it's a holomorphic one form, and then I can integrate against its conjugate, so it's like dz bar, and that gives me a metric at each place. So, but the great thing about elliptic curves is the following fact, that when you take the 12th power of the canonical bundle, there's a sort of canonical 12 form on each elliptic curve that's essentially given analytically by the Ramanujan delta function. Okay? And so because this guy has a canonical metric, it really is an invariant of this elliptic curve. Okay, so it seems like, this used the fact that I have this sort of model for E over the ring of integers, but in fact, it's got an independent of that as well. So it's actually an invariant of the elliptic curve. So this the arithmetic degree of this metrized line bundle is invariant. And because I have this section over here, this trivialization, if you go back and look at this part of it, because it's a trivialization, there's no contribution, so to speak, from the finite places. So you have this infinite contribution and the finite contribution. And if this is all of M, then you only see the infinite contribution. Okay? So this is basically just the infinite contribution that you can work out. And it's a pretty simple computation. And it yields this result. So this tau here is basically some representative for the lattice. So every elliptic curve with complex numbers is C mod a lattice. And you can represent a lattice by an element of the upper half plane. And that's essentially what this is. And this here is just the usual Ramanujan delta function evaluated at that point in the upper half plane. Okay? So now, to go back to the Challis-Elbert formula, so remember we have this imaginary quadratic field K. So if E has complex multiplication by the full ring of integers, and in this case, so I'm lying a little here, but anyway, you can take L to be the Hilbert class field. So the reason I'm lying a little is like it's not guaranteed that E has a model over the full ring of integers in the Hilbert class field, but that's okay. It's like any case. So then the Hilbert class field, I mean, it's Galois group over K. It's just the class group. So that's classical complex multiplication, so each of these lattices is going to be homothetic to a lattice that's corresponds to a fractional ideal of K. Okay, and you can kind of use this, and so this is essentially just follows from the theory of CM elliptic curves. that you can reinterpret this right-hand side as this. Okay? So you put this all together, and what do you get? You get this interpretation of the Chauvet-Selberg formula. Okay? You have an elliptic curve with Cm by OK. Then its Falting's height, just kind of defined by this sort of canonical metric on its canonical bundle, is given like this. Okay. All right. So note in particular the left-hand side. So because the right-hand side is independent of the choice of elliptic curve, it tells you that the left-hand side is also independent. Okay, this is not so hard to see for elliptic curves, but we'll see later this. When you generalize this as a non-trivial thing. Okay, questions? Oh, it's the Dirichlet character for K. So it's from just the quadratic character associated with the quadratic field. Yeah. Yeah. So it depends only on K. Okay, so this can be generalized, this story, to Cm abelian variety. Okay, so you get an elliptic curve by taking C mod a lattice. You got an abelian variety by taking C to the G mod some appropriate lattice with some properties. And so you have, okay, here's a slight switch of notation. My E is no longer a geometric object. It is now a Cm field, okay? And now, from now on, E will never appear as an elliptic curve. Okay, so it'll always be a Cm field. And F is its totally real subfield. And then for so any embedding of L inside the complex numbers, I can look at the de Rham homology of the abelian variety. And because A has Cm by Cm by E, this is going to break up into these pieces, these H sigmas, each of which is one-dimensional. Okay, that's sort of the story. And the Lie algebra is going to pick up some of these, exactly half of these one-dimensional pieces. Okay? And so this phi here is what's called the Cm type. It's a subset of all the embeddings of E inside the complex numbers that, together with its conjugate, gives you the full set. Okay? And once again, its canonical bundle, which is now the bundle of top degree forms, top degree algebraic forms on A, is equipped with a metric, again, provided by integration. You integrate against its conjugate. Okay? And when A has good reduction, which is always the case up to extending L to a finite extension, if you have a Cm abelian variety, then it always has good reduction over some finite extension. Okay, so we can always assume this. And then this, if you take the canonical bundle now of this abelian scheme, that gives you a metrized line bundle over OL. And you can use this to define the Falting's height of A. So once again, note that the right-hand side seems like it depends on the cynical model, whereas the left-hand side, by notationally, it only depends on A, and it's well defined. So here's the theorem of Colmez. So just like with the elliptic curves, so the Cm type for elliptic curves is really, it doesn't carry that much information. So because you have a quadratic extension, then there are only two embeddings, each conjugate through the other. So there's basically, up to the conjugation, there's essentially only one Cm type. But in this situation, the Cm type is sort of a non-trivial invariant. And so Colmez showed that the Falting's height is actually an invariant of the CM type. Well, so the faulting site doesn't depend on L because there's a normalization by the degree of L. So in fact, the faulting site is all, by definition, insensitive, the way I've defined it to field extensions. But it actually doesn't depend on A. So you can choose any abelian variety over L with CM by OE, and that's CM type. And you get the same answer when you compute its faulting site. And this is, so this is non-trivial. That's enough. Okay, so one natural question, in knowing this, is if there is some way to define some sort of arithmetic invariant of E and phi that is the analog of the right-hand side of the Challis-Selberg formula. And so this is a problem also solved by Colmez. So I'm not going to tell you the definition, but he defines a function, all right? And what kind of object is it? So he defines this linear combination of Artin characters which satisfy this condition. So this condition basically ensures that the L function of chi is, it's a priori, it's a meromorphic function on the plane. But in fact, at 0, this ensures that it has no poles or zeros. And so Colmez defined a canonical linear functional on the space of all such linear combinations, and whose value on this particular guy is the Falting's height so I wrote Falting's height of E phi. What this means is Falting's height of any abelian variety with complex multiplication by OE and CM type phi. Okay? And so essentially the point is that there are many relations between functions defined in this way. So first of all, these functions generate the set of such linear combinations. And furthermore, the relations between them are respected by this functional. So he used this now to define essentially the other side of a Challis-Selberg formula. So there's a functional you can define, as I said. So this L0 chi is a non-zero quantity, and it makes sense. So you can look at this functional on these Artin characters, where this is the Artin conductor. And so you can extend this to a functional on the space of all such linear combinations, and so that you can call H Colmez of E phi, and that's evaluated at this linear combination. And he conjectured that, in fact, this is the same as the functional given by the Falting's height. Okay, so this would be essentially a full generalization of the Challis-Selberg formula. Okay, what is known? So, as I said, so when E is quadratic, then this is the Challis-Selberg formula. When E is abelian, so in the same paper where Colmez studied all these things, he proved that the conjecture is true for an abelian extension. It's essentially it's cyclotomic. So there's up to some factors which are removed by Obus, but this proof essentially follows ideas, expands on ideas of Gross. So Gross he reproved the Challis-Selberg formula using geometric ideas, and the same ideas were used here, essentially. And so the thing that's most relevant to this talk actually is, so there was an idea of Tonghai Yang that he used to prove the conjecture And I'll say a bit more about this as we go forward when this is a quartic, when E is quartic. But the thing I want to talk about, I guess, the thing I'm supposed to talk about, because this is what the prize was awarded for, is this theorem, which says that Colmez's conjecture is true when averaged over all CM types. So CM of E is all possible CM types for E. And so what you can do is you can take both sides of the conjecture and sum them up as you vary over all CM types. So for instance, if the Galois group of the normal closure of E acts transitively on the set of CM types, sometimes that can happen, then this is equivalent to the full conjecture. But in any case, so this is work, Andreatta, Goren, Howard, and me. And there's another independent proof by Xinyi Wan and Shou Zhang at the same time. So, and the reason why this is, in some sense, approachable, as opposed to a general conjecture, which is that the right-hand side is really simple. It's somehow only involves one L function. Now it's a very simple one. It's an abelian L function for the quadratic extension E of its totally real subfield F. Okay, so sort of hard to get simpler than this. And the rest of them are just this is the discriminant and so on. And so this is to say that somehow the ideas used in sort of the proof of the average conjecture have no hope of working in general. We just don't know enough certainly about the left-hand side, but also not so much about the right-hand side in general. But in any case, so here's a sort of idea of proof. Quickly. So the idea is to, first of all, reinterpret the left-hand side as the height of a single abelian variety. So I'm not going to give any of the details on this slide, I'm afraid, but just to give a feel of what happens, what goes into this. So more precisely, the point left-hand side is actually, even though seems like it's a sum of things, it's a sum of periods or sum of heights, is in fact the height of a single metrized line bundle. And this is essentially a combination of an observation of Tonghai Yang, so I'll tell you a bit about this. So the point is that there is, so you have this abelian variety with CM, or you have these CM types. Okay. So there is a single metrized line bundle on some OL. I won't say much about what this OL is. So you can think of this as being some kind of arithmetic curve. Okay. And it maps to a larger scheme. So in this case, this is a Shimura variety, this M over here. And so there's a canonical metrized line bundle over this larger variety, okay, that when you pull back to this arithmetic curve, its height there, its arithmetic degree, is computing the left-hand side of the averaged formula. And in some sense, sort of this is a little sort of ahistorical. So the point is this kind of thing was observed by Tonghai Yang when he was working with quartics. So he noticed that there was a particular line bundle on a particular sort of Shimura variety where he could compute its height. And he noticed that this was actually related to the Falting's height of some CM abelian variety. And then you notice that you could prove Keerthi-Colmez conjecture in this way. And so essentially what we did was there's a whole class of Shimura varieties to which Tonghai Yang methods apply. And so we just basically pulled back his idea, and we asked, what is it computing on this side? And it turned out it was computing the average height of abelian varieties with CM by sort of this fixed thing. And anyway, so as I said, this observation is essentially due to Tonghai Yang, so the point is that the left-hand side of the average sort of formula is an arithmetic intersection number. I have this metrized line bundle on M, and I'm intersecting it with this arithmetic curve, C. And so the next step, which is related, and I'm going to kind of use it as a Trojan horse to move into the next part of my talk, is this fact, which is that this omega hat is actually a constant term in a generating series of special cycles. So these arithmetic special cycles, which are valued, so this is a Q series valued in the arithmetic Picard group of M. So I didn't explain what a metrized line bundle is on a general sort of scheme over a number field. But it's essentially it's the same definition as for OL. You're just introducing continuous families of metrics over each of its complex fibers. But in any case, so you have this modular generating series of special cycles where this omega hat is the constant term. Okay, so this modularity means something. Okay, it means something particular, but what it's actually saying is that there are a lot of relations between the coefficients over here. So there's whatever a modular form is, this is going to be a modular form of a fixed weight. And so these coefficients that you see over here are all going to live inside some finite dimensional subspace. And so even though you have infinitely many of them. So that means that there are going to be lots of relations between them. And so you can kind of exploit that. So we have, in particular, a simple way to think about this is that if you have sort of just a usual modular form, and you know all of its coefficients except the constant term, then you know the constant term. That's just the, okay? So this tells us that basically what we try to do is like compute all these other guys instead. So instead of computing what the constant term is doing, which it is essentially would be proving the result, you compute all the other contributions that, and the reason this kind of is doable is because these guys are given essentially a moduli problem. And so you can use that moduli problem to study what's happening. Okay, there's some technical comments on what the proof is. But the main thing is that there's a crucial role played by the Siegel-Day formula, which is it's a result in representation theory, in particular in the theory of theta functions or of the theta lifting in general. So essentially they mean, the reason you have both these names is Siegel, it's the part of this, a special case of this is what's called the Siegel-Maas formula. And then they gave a quite extensive generalization of this result. Okay, so this is all I'm going to say about the proof. In any case, I think I only have like 15 minutes left. So I want to talk about sort of this aspect of the story, just like this modular generating series, But before I do that, any questions about this? I'll say more about that. Yeah. Yeah, well, not really. But so these are going to be Shimura varieties associated with quadratic spaces of signature N2. So, okay, that's kind of like what happens here. Okay, so I want to say, so I want to focus on this theta part of the story. Okay, so here's sort of a general kind of thing that you know, when Weil in his paper where he basically constructs a Weil representation, one of the things, okay, that you can extract from it is the following. I think it's basically a classical result, but okay, but maybe in this formulation, due to Weil. Okay, what is this? So you have an associative algebra, has a positive involution, and you have a positive definite Hermitian space, a Hermitian form. Okay. Now, if you have any n tuple, you can define what's called this moment matrix, which looks like that. It's a Hermitian matrix with respect to that involution. And then you can write down this formal Q series where, okay, if you just kind of collect the terms together, so this, you get this the representation number, kind of that's weighted by this Schwartz function. So I think I skipped something on this page. So what is this naught? This phi naught is a Schwartz function on the adelic points of W naught. So that will show up on the next page. So this is an adelic formulation of a very classical construction of theta function associated with positive definite spaces. Okay? And so what we know, and this is, and this generality is due to Weil, that this functional that associates with, sort of if you take the Schwartz function, I'll explain, okay, maybe I should just write this here. So this is some kind of version of the Siegel upper half space. So if you want, if you take D to be Q and N to be 1, then this is just the usual upper half plane. Okay? And so you have some function on some version of the upper half plane that depends on this parameter, comes from a Schwartz function. And you write down this generating series in this way. And they proves that this is automorphic of a certain weight for this, okay, this group. So as I said, if you take D to be Q and N to be 1, the split unitary group is just SL2. Okay? So you have this thing. And what it's modular with respect to, so this is automorphic. What does automorphic mean? Automorphic means that it satisfies the reciprocity law. Well, it means two things. It means, first of all, that this right-hand side converges, which is not so hard to show in this case. But beyond that, it means that it satisfies the reciprocity law. So there's an action of the rational points of this group on the space and also on this space. And this has to be invariant for that action. Okay? So I don't know. So that's a definition of modularity. We'll see. Okay. Okay. So the proof of this involves two things. Okay. I mean, this is okay. It's not relevant for this rest of the talk. I don't think I have time. So anyway, so there are two aspects of this which would be relevant if you want to generalize this. Okay, so what happens now instead if you have an indefinite Hermitian space? For example, the quadratic space of signature N2. Then in that case, well, there's a generalization of the Siegel-Weil formula for that in a representation theoretic direction. But for my purposes here, what's more relevant is that Kudla and Milson observed, I mean, following the work of a lot of other people, but okay, in this generality was due to them, that it's possible to write down, instead of these representation numbers, you write down actually cycle classes or cohomology classes on locally symmetric varieties. And so what they showed is that what you can do is if you have a Schwartz function, Or if you have this W, you can associate some locally symmetric space, so it's a quotient of some symmetric domain by an arithmetic subgroup of its, okay? And have these cycle classes in the cohomology, so when you write down this generating series in like analogy with the representation of numbers, this is also automorphic in the same way as that generating series I wrote down before. But what does this mean? So it takes values in a vector space. It's not valued in C. So this means that coupling against any class and complementary dimension here yields a convergent series. It's an automorphic in the sense that I explained before. So you get a whole family of automorphic forms indexed by this cohomology group. Or rather, it's dual. What is not a finite sum? It's not finite. It's over all these Hermitian matrices. So it's the same sum. It's the same summation as before. So you're just summing over all possible. This is finite adels, yeah. Yeah. I mean, there's this k over here. So this k is some level that it's implicit, but because I'm dealing with a geometric object, you can't really define it on the full Schwartz space. Anyway, this is some technical part. Okay, so what are these special cycles? The point is that this locally symmetric space is a space of basically Hodge structures of weight 0. And the special cycles are the fundamental classes of what you can call Noether-Lefschetz loci, so where these Hodge structures pick up additional Hodge cycles with prescribed moment matrices. So here's basically one example. So if you take D to be Q and W to be this space, so this is basically a split quadratic space of signature 2, 1. Okay? So in this case, MW, so what is it? It's just the modular curve. Okay, so it's a space of Hodge structures of weight -1, Q2, or Z2, up to SL2Z action. Okay, and so we just have the modular curve. And what is this guy doing here, right? So this is the space of essentially trace 0 endomorphisms of the homology of the elliptic curve. And the loci where it picks up Hodge cycles are the loci where the elliptic curve has non-zero trace 0 endomorphisms. That's exactly having CM. That's what it means. Okay? So in here the level is just SL2Z hat. So you have to be a little careful. So this tells you what the cycles are when you're dealing with sort of positive moment matrices. But when it doesn't really, there's no moduli problem that gives you like a non-trivial cycle when you just ask for endomorphisms, of norm 0. It's just a 0 endomorphism. Okay. Anyway, so that's okay, so what's relevant here is that because these classes come from fundamental classes of sort of these symmetric spaces, locally symmetric spaces, when MW has an algebraic structure, namely, which means that it's a Shimura variety, these special cycles are also algebraic. And so in fact, you can lift the cohomology classes to Chow classes. And so this conjecture is essentially due to Kudla, maybe not like in this generality of this D and whatnot, but it's basically due to Kudla. And what he said is, okay, you just write down the generating series of Chow classes in the same way, where now, okay, you replace the right-hand side here, which was used to be the cohomology group, and the cohomology group is, a very nice object in general. Whereas this Chow group, okay, you don't have very much information about it in general. Okay, so it's just a vector space. And so he defined this guy here, and he conjectured that this is also automorphic of the same weight. So we essentially have this progressive generalization of, okay, in this generality, almost nothing is known about the modularity of the generating series. When W is a quadratic space of signature M2 and N is just 1, so you're just talking about SL2 modular forms, Borcherds gave a proof, and it's miraculous. Like it uses his Borcherds products and has no hope of being generalized anywhere. But you can take Borcherds and you can kind of run with it. So it was done by Wei Zhang and Bruinier Raum, and they just kind of bootstrapped up from n equals 1 to all possible n, still with this condition on W. And there's also another kind of the same bootstrapping argument was also, you can, okay, replace cube of totally real field, and okay, this was done by Yuan Zhang. But if you think back to what so that when I said we had this arithmetic series that was modular. So this is all a geometric theory. In fact, this theory in this way I've done it over the complex numbers. But there is a, okay, let me just kind of, okay, blah, blah, blah. So this Shimura variety, so this quasi-projective algebraic variety, it actually descends over a number field. And okay, over the past many years, maybe 10, 15 years, there's been a lot of sort of progress in constructing integral models for these objects. And so there's in particular, okay, so this condition called abelian type, which means essentially it's some moduli of motives that come from abelian varieties. In that situation, you have an integral model. And okay, here's the theorem. The functional that was defined over the complex numbers can be extended or descended, extended to this integral model. Okay. This is surprisingly already new for the modular curve. And the reason for that is that, okay, like what is one example of something that lives on the left-hand side? So if you have a modular curve, then as I said, this is just somehow the space of trace zero matrices, and that's just GL2Z hat. So what's an element on the left-hand side? Okay. Take any sort of random matrix, or 2 by 2 matrix, mod p to the n of trace 0 mod p to the n, and take its conjugacy class, and take the characteristic function of its preimage in Z hat. That's an element on the left-hand side. Okay, now I want you to do it a one cycle on the curves. So it's some kind of problem of writing down a parameter space of moduli of sort of Heegner points that parameterize endomorphisms with a given characteristic polynomial mod p to the n for some n. And this turns out to be like a very tricky thing to analyze in general. So I don't know how to do it by hand. So because this is some general result that in a special case gives you that thing, but I don't actually know how to analyze that guy by hand, which is okay. It's just an interesting observation. Any case, so you have this canonical functional. Okay, now you can make some conjectures. I'm running out of time, so I'll just say, okay, it has some nice properties that you can show. It's sort of satisfies automorphy with respect to a pretty large subgroup here, but okay, it turns out like that's not the interesting part. The interesting part is has to do with z goes to -1 over z essentially when you want to show modularity. That's the hard part. That we don't know how to do. We don't know how to show that this is convergent. Anyway, so this is. So on. So okay. All right. Okay. So the main thing here is that these classes are constructed as virtual fundamental classes of derived cycles on the Shimura variety. So this actually is a construction that uses derived algebraic geometry. I don't know how to do it without that. And okay, let me just leave you with some slogans that I find helpful when I think about this story. Okay, first slogan, Shimura is a Mailai space of motives. Okay, well, it's like that's a way to think about them. Second slogan, okay, these special cycles are these noto-Lefschetz loci where certain weight zero motives, like they pick up additional sections. So you have additional endomorphisms. There's a analog of like moduli K3 surfaces where you pick up additional Picard classes, and so on. Okay, here's something completely speculative, but motives over S are secretly just vector bundles or bundles on some other stack. There's a talk by Peter Schulze, like there's an IHES talk. You can see it's called Ring Stacks for Motives or something, where he kind of talks about this. Okay, and so last slogan. Okay, special cycles are loci where some bundle somewhere picks up additional sections. Okay. Okay, maybe I'll tell you why. Go to one more slide, and then I'll finish with this. Okay. So the reason that this actually is a reasonable kind of slogan to have is that there are local versions of this stack of motives. Okay, so there's a construction of sort of every sort of p-adic ring. You can associate this stack called the syntonification. Okay, it's a complicated thing, but one fact about it is that the canonical equivalence of categories between vector bundles on this sort of complicated stack with satisfying certain conditions and Petersburg groups. So in that sense, so this is like the philosophy of motives being bundles on some stack is being realized here. Okay, so this is some precise analog of the equivalence that you have for complex manifolds between families of complex tori and sort of this. Okay, maybe I'll just finish this up. So, okay, this is some complicated looking theorem, but what it's basically saying is that this idea of cycles arising by taking sections of bundles does work locally. So you take a bundle of rank D over this complicated stack, and it has some conditions on its hot state weights. And what you can do is basically you take its cohomology, all right, which amounts to taking its sections. So then it's represented by sort of cycles in some sense. The cycles have virtual dimension controlled by this hot state weight space. So these are the local avatars of the cycles that we are interested in. And we can kind of glue them all together to get the global cycles that go into, whose classes give me the cycle classes from the theorem that I stated earlier. So this is what I mean when I say that I don't know of an elementary way to construct those classes even for a modular curve. That kind of goes through all of this. It'd be nice to give a more direct construction in that case. Anyway, I'll just stop. Thank you.
Thanks for a wonderful talk. Any questions, people? I have a very nice question. So in the earlier part of your talk, you mentioned that the general component conjecture is very rich.
Yeah.
So is there any possible examples within the product case or the case that either side of the conjecture can be computable?
I think there's some like optics. So I like a few years, maybe during COVID, I did some like summer project with some undergrads where they computed the right-hand side for some octet CM extensions. And there's like the first non-trivial case, but I don't remember the details. I can send it to you later if you're interested.
Send me comments.
Yeah, exactly.